Okay, so fix a language. So again, we have L formulas, L sentences, as for language of rings. Okay, maybe one difference. So one new thing. So how the relations come to the formula. So if, for example, if R is in R, and let's say an R is 4, so RT is 4, and some C1, C2, C3, C4 are constant symbols, then this is a formula. Actually, it's a sentence. And such are. Okay, so now I'm a bit defining what is it. And if, for example, if F is in F, let's say, and F is 2, then such a thing, this is not a sentence, because it just says function of, but what? So this is not a sentence, not a formula, sorry. But saying this, f of this equals something else, this is a formula. So just several examples, because before we didn't have this relation symbol. So I want to say this. So, okay. So even more, e.g., this is LOR sentence. Because this is binary relation symbol, which may be true. Okay, about the truth I didn't talk yet. Okay, so next week we will prove compactness theorem. And for that, so more set theory, sorry. Cardinalities will be important. So by cardinality of the language, okay, we don't mean just 3, which will be here. We mean sum of these 3. So if any of them is infinite, it's a maximum. It will become important, like in this theorem Osler mentioned in the break, that you can find countable something. Then such counting will be important. And, okay, our first lemma, we will not give proof, because we didn't define precisely what are formulas. So the set of L formulas has cardinality. Yes, these formulas are obtained in finite ways from the symbols. So you can get what is cardinality. It's the same as maximum. So in any finite step, so definitely there are at least I'll have 0 of them, but there may be more. This will be used later. Okay. And again, about constructing sentences. So if x1, xn is an L formula, and something like what's happening kind of here, C1, Cn, so these are free variables, are constants, then this is a sentence. Yes, if we replace free variables, those non-quantified ones, by some constant symbols, we get a sentence. Okay, and one more last formal thing. Now we have this language and take arbitrary set, some more sets. So for any set A, we have new language. LA. So we add new constants from this set, which is F R CA, where CA is alt C. Okay, let's say disjoint, and new constants coming from this A. This will be used if we want to talk about something which needs extra parameters. So this, and then LA formulas are sometimes called L formulas with parameters from A. Usually this A will be coming from some model, will be a subset of a model of some theory. Okay. So this was all about this abstract string of symbols in this general case when we have arbitrary language. So now again we want to give meaning. So I want to talk about structures. So an L structure. So we have to interpret all of this. This we have to interpret as actual functions of arity as this NF tell you. This we want to interpret all elements of curly R as actual relations and constants as actual elements. So L structure is a set M together. So as I said, everything naturally interpreted. A function so real function, actual function Fm from M to power NF for each function symbol, a relation, so a subset. Yes, relation is a subset of Cartesian power. And finally, an element Yes, so everything, all these abstract strings of symbols now have some meanings in some set. And then, as before, this is this is universe, and those are interpretations. And this is L structure. So everything as before, just there may be many more things to interpret.
Can I
Sure.
Except the constants, there is no elements in the universe, right? So you define an element as a constant. So
There may be. I mean, there may be no constants in the language.
except the elements from the constants, there is no elements. So by definition of it, right? I mean,
No.
if we take an element from the universe,
Yes.
by this definition, this cannot be. This may not be an element of by this definition, but I couldn't understand it.
But for example, we have that R. Well, okay, this looks a bit strange, but we have real numbers. So this is the real 0, 1 in R.
Yes.
These are constant, but everything else also exists.
I know it exists, but in this definition, an element, by this example,
I know, and he doesn't say an element must be of this form. He says it assigns an element for every constant symbol in this.
So this element is still for together with.
For every C in C, there is an element in M. It doesn't say all the elements are of this form.
Oh, okay.
Yes.
So,
A function.
So I'm still finishing a sentence together with a function, a subset, an element. That was still.
And there are many other functions, of course.
Yes, and there are.
Yeah, I mean, there are other functions, there are other subsets, but it
Sometimes people say that we interpret set theory if they take the language such that all functions and all subsets are interpretable. They can do such a thing. So from a set, you can create a language just naming everything. All the functions from the set, all the relations. And then sometimes people say this is like interpreting set theory, but but this is not very natural. Okay, yes, so there were just some picked constants. What then? Some examples. So again, okay, maybe I'll just write here. So if C is an L sentence and M L structure, then as before, this means that he holds M. Yes, there is always a way to check, to understand whether a given sentence, even L sentence, is satisfied or is not satisfied in a given L structure, as we were checking in the case of rings. Okay. Shit. I wanted to give example. Okay, so maybe we interpret a real plane as an L vector structure. This is so it is so I erased it, so let me recall. This was plus, minus, Okay, so things will start to look strange, but so what is plus? So, okay, AB plus in the sense of R times R. Okay, maybe when this is addition in R, which we of course never write with this superscript R, but let's do it. Minus R minus R times R. And of course, lambda R interpreted R times R of some pair AB. This R and 0. So this was probably most important, how to interpret in vector these unary functions in an actual vector space. And example of sentence. So for example we have Q. Okay, so maybe of course normally we write for AB in R A plus B and not A plus RB. So often in reality,
in the left side of the board, you construct a new language for R times R vector space, right? You construct it from the L vector space R, this language, and you construct a new language, right?
No, I'm constructing, okay. So I'm saying that R times R, I interpreted symbols from this language in the set R times R. I didn't construct a new language.
But in this language, this is a language of the vector space R
over R.
Yes. And now we are working on a new vector space R times R.
Which is a vector space over R.
Yes. And
so it is an L vector R structure.
Shouldn't we write L vector space R times R?
But this is the field.
Okay, sorry.
Okay, so this is like V. This was the vector space, the easiest one. Okay, so maybe I just say, so in practice, okay, even if we have interpretations of these symbols, in practice we don't write this interpretation on the top, we write the same symbol as for the abstract symbol. So we forget about all of this which was said, because usually it has some obvious meaning, so we don't put this R upstairs. Yes, so actually this superscript, they will be very quickly forgotten, and it will be always somehow understood what is a particular interpretation in a given universe of the symbols. Okay, like in the group, we don't write group operation with some superscript G, we just write always the same dot. So here it's a similar thing, but it may be confusing at first. So now I will do the same thing. Yes, so now I'm not writing this Q. This is the usual order on Q. So this is LO structure. And I'm just going to write a sentence which it satisfies. So it satisfies the sentence that for each xy there is z such that if x is smaller than y, then x is smaller than z, and z is smaller than y. So basically it says that the order Q is dense. So this is a property which can be expressed by this kind of sentence, that between any two elements in the order, there is another one. This z, if one is smaller than another, we can put so this is an example of a sentence which is true in Q, but for example it is not true in Z. Because there is nothing between 0 and 1. Okay, so there are some examples of L sentences which may be true or not in given structures. Okay. So some more definitions, and then I will finally get to compactness theorem, but probably it will be the end. One more example. So this yes, this is R is an ordered ring. So this is R OR structure. And it satisfies a sentence saying that if x is a square, then x is greater than 0 or 0. So sentence says squares so this is another example of a sentence in this particular language, which is true in this particular structure. Now, from any structure, we can create a theory. So let M be L structure with universe M. And this will be important case when this new language will be used, and A be a subset here. Then we create a new language. Okay, then, sorry, the language is the same, LA, but then M is still LA structure. In obvious way. So just any of these constant symbols CA is interpreted as A. Nothing very intelligent, but this is like fixing some new set of parameters we want to focus on. And finally, we define the theory of M This will be the set of all sentences and which are true in M, and sometimes it's important to specify parameters, so all the same with these extra parameters. So this is theory of this M with parameters from A. Okay, and one more definition which gets us closer to these things we need for access theorem and Nullstellensatz. When we have tool structures, then we say they are elementary equivalent. Elementarily so actually it's something like isomorphism but weaker, much weaker. So notation is like this if they have the same theories. Kind of they are the same from model theoretic point of view. Everything which is true in one structure is true in the other. So if you remember the model theoretic theorem which was used to prove in Axe theorem, it was something similar. It was talking which sentences are true. It was describing which sentences are true in complex numbers in terms of which sentences are true in this field's FP-Alge. It's not exactly this, but it is very related. So now I have two problems for you. So the last two problems for the first problem session. First one has two parts. Second is generalization of first. So let L, this is language of groups. So obviously this is binary function symbol, this is constant symbol. So find a sentence such that for all groups G we have that G satisfies the sentence actually if and only if it is isomorphic, let's say, to Klein group. Now isomorphic, but it's important that this group is finite. And part B says that Klein group, or even being a group, didn't matter here. So generalization of A we can do the same in any language and for any finite structure. For any finite language. Okay, yes. So L, a finite language. M, finite L structure. Okay, maybe not find, so show. Okay, so here I'm telling you find. So write down a sentence. Here I'm saying just show that there is a sentence. Such that for all L structures N we have that N satisfies this phi if and only if N Okay, now I noticed I didn't define what is isomorphism of structures in general. Sorry. So also and try to define what does this mean in general. Or take L as language of groups. Yeah. Taking problems from the book, somehow always you have to remember if I defined everything. So I didn't define what is isomorphism of arbitrary structures, so you can just do it in this case. Or try to find a definition which is natural and do it in general. And last problem maybe it will be it. So something for elementary equivalence. So in language of groups, show that Z plus is not elementary equivalent to yes, so you have to find a sentence. You have to find a sentence in the language of groups which is true in integers and not true in integers times integers. So something more down to earth. Okay, so it may be a good moment to stop. Okay, so next week we will show a theorem. Okay, we will show something called compactness theorem, which says that if we have a theory such that any finite part has a model, then the whole theory has a model. And with this theorem, we can conclude some other general theorems, which will give us these things we needed for access theorem and Nullstellensatz. So this compactness theorem is always crucial, and we have to always start from this one. Okay, and then so anyway, you will see next week. So that's it. Thanks. And